You may have heard of the carbon cycle. The process by which carbon moves between different reservoirs on Earth, such as the atmosphere, the oceans, the biosphere, and the lithosphere. The carbon cycle is crucial for life on Earth, as it regulates the concentration of carbon dioxide in the air, which influences the greenhouse effect and the temperatures of the planet. One of the key components of the carbon cycle is the weathering of rocks, which is the breakdown of minerals and organic matter by physical and chemical processes. Weathering can either consume or release carbon dioxide, depending on the rock type and the conditions involved. And in this episode, we're going to talk about a fascinating study that reveals how the weathering of rocks on land can affect the global carbon cycle and climate. This new process has been hiding in plain sight for decades, and scientists are now saying it's had major impacts on Earth's climatic history and may even be a contributing factor to how Earth's climate will evolve in the future. So sit back and relax, because this one's going to be interesting. I'm your host, MrEarthGuy, and you're listening to Earth SciShow. One type of weathering that consumes carbon dioxide is silicate weathering, which involves the reaction of silicate minerals with water and dissolved carbon dioxide to form bicarbonate ions and other dissolved products. These bicarbonate ions are then transported by rivers to the oceans, where they can precipitate as carbonate rocks such as limestone. This way, silicate weathering transfers carbon from the atmosphere to the lithosphere, acting as a long-term sink of carbon dioxide. Silicate weathering has been considered as a stabilizing feedback mechanism for Earth's climate, as it tends to increase when the temperatures and precipitation increase, thus removing more carbon dioxide from the air and cooling down the planet. This feedback has been invoked to explain how Earth has maintained a habitable climate for billions of years, despite changes in solar luminosity, continental configuration, and volcanic activity. However, there is another type of weathering that releases carbon dioxide, which is the oxidization of organic carbon in rocks. Organic carbon is carbon that was once part of living organisms such as plants and animals. Some of this organic carbon can be buried in sedimentary rocks such as shales and mudstones, where it can remain for millions or even billions of years. This organic carbon is called rock organic carbon, or OCPetro for short. When these sedimentary rocks are uplifted and exposed to the surface by tectonic activity or erosion, they can undergo weathering by oxygen and water, which can oxidize the OCPetro and release carbon dioxide into the atmosphere. This way, OCPetro weathering transfers carbon from the lithosphere to the atmosphere, acting as a long-term source for carbon dioxide. OCPetro weathering has been largely overlooked in studies of the global carbon cycle, as it was assumed that OCPetro was inert and passive in the shallow subsurface. However, recent evidence suggests that OCPetro weathering is far from negligible and may rival or even exceed silicate weathering in terms of its impact on atmospheric carbon dioxide. In a new study published in Nature, a team of researchers from Oxford University and other institutions have quantified for the first time the global flux of OCPetro weathering. This was done by using a novel approach based on a trace element called rhenium. Rhenium is a rare metal that is associated with OCPetro in marine sediments, and is released as a dissolved oxyanion when OCPetro is oxidized during weathering. An oxyanion is an ion containing one or more oxygen atoms bonded to another element, such as sulfates or carbonate ions. By measuring the concentration and flux of rhenium in rivers around the world, and comparing them with estimates of OCPetro content and denudation rates in different regions, the researchers were able to calculate how much OCPetro is oxidized and how much carbon dioxide is released by this process. And for those wondering, denudation is a geological process which moving water, ice, wind, or waves erode the Earth's surface, therefore leading to a reduction in elevation. The results are surprising and alarming. The researchers found that OCPetro weathering releases about 68 megatons of carbon per year as carbon dioxide from land surface environments. This flux is similar to or even higher than the global flux of silicate weathering, which consumes about 94 to 143 megatons of carbon per year as bicarbonate ions. This means that OCPetro weathering offsets or even overcomes silicate weathering as a sink of atmospheric carbon dioxide at the global scale. The researchers also found that OCPetro weathering is highly concentrated in certain regions where sedimentary rocks are abundant and erosion rates are high. These regions include mountain ranges such as the Himalayas, the Rockies, and the Andes, where OCPetro oxidization rates can be up to 10 times higher than the global average. In contrast, regions with low erosion rates or low OCPetro content have negligible or negative OCPetro oxidization rates. The implications of these studies are profound for our understanding of Earth's long-term carbon cycle and climate evolution. The researchers suggest that OCPetro weathering may have played a major role in regulating atmospheric carbon dioxide levels over geological timescales, especially during periods of intense mountain building and erosion. For example, they propose that OCPetro weathering may have contributed to the rise of atmospheric oxygen and the cooling of the climate during the Paleozoic era. This is between 538 and 251 million years ago, when large amounts of OCPetro were buried in marine sediments and later exposed by the formation of the Appalachian and Caledonian Mountains. The researchers also point out that OCPetro weathering may have different responses to climate change than silicate weathering, as it depends on the supply of OCPetro by erosion rather than the kinetics of mineral dissolution. This means that OCPetro weathering may not act as a negative feedback to global warming, but rather as a positive feedback that amplifies it. For instance, OCPetro weathering may increase with temperature and glacial erosion in high-altitude regions, releasing more carbon dioxide to the air and further heating up the planet. The study also raises questions about the balance of carbon fluxes between the atmosphere, the biosphere, and the lithosphere, and how this balance may have changed over time as life evolved and the OCPetro stocks of sedimentary rocks increased. The researchers suggest that other components of the carbon cycle, such as the burial of organic matter in ocean sediments and the degassing of carbon dioxide from volcanoes and metamorphism, need to be revisited to account for the large influx of OCPetro weathering. This study is a remarkable achievement that sheds new light on a previously neglected aspect of the carbon cycle. It challenges our current view of how rocks weather and how they affect Earth's climate. It also highlights the importance of OCPetro as a major reservoir of carbon on Earth, comparable in size to that of soils and marine sediments. This study shows that OCPetro is far from inert and that its weathering has profound consequences for the global carbon budget and climate stability. And that's all for today's episode. I hope you learned something new, and if you did like this episode, please share it with at least one friend. It really helps the channel grow. Don't forget to subscribe and follow on your favorite podcast platform. You're listening to Earth SciShow, and I'm your host, MrEarthGuy. And remember, stay curious.